Hello, this is John Miyares, and in this lesson, we're coming back to Chapter 12 and looking at Section 12.6. The main focus of this section is something called the Binomial Theorem, but we're also going to look at something called Pascal's triangle, which is not only connected to the Binomial Theorem work we'll be doing in this section, but is also connected to the combinatorics work we looked at in Section 14.1. This material that I'm about to present is taken from the top of the notes packet from Pascal's triangle. A very interesting number pattern with unexpected applications is called Pascal's triangle, named after French mathematician and philosopher Blaise Pascal. To build this triangle, we start with the number 1 at the top and continue placing 1s along the outermost diagonal sides as in this pattern shown here. The values of the interior numbers are based on the 2 which came above it. The top row, with just the number 1 in it, is labeled as row 0. The second row, labeled row 1, should have 2 1s in it. The first entry in each row is actually going to be labeled the 0th entry. In any given row, for example, the 8th row of the triangle will have actually 8 entries in it, but we're going to call it row 7 and have the first entry be the 0th entry and the last entry be the 7th entry. This will make sense as we progress. Here is our triangular grid that we're going to be filling in with the values of Pascal's triangle. In the textbook, they define the expression with this n over r in parentheses as the value of row n and entry r of this triangle. If that wasn't confusing enough, as I mentioned in the previous slide, we're going to mark the top row as row 0 and the first entry in each row as entry 0. Also, as we said in the previous slide, we're going to start with a 1 at the very top. This will be considered row 0, entry 0. From there, we're going to put 1s all the way down to the outside so the first entry, or entry 0 in every row, is going to be a 1, and the last entry in every row is also going to be a 1. So in row 1, which is the second row, we're going to be just 1 and 1. In the third row, which we're now calling row 2, we start with a 1 on the left end and a 1 on the right end. And this pattern is going to continue all the way down the outside of the triangle. Now we need to start filling in the blanks in the rest of the triangle. Let's look in row 2, which is the third row of the triangle and starts with a 1, ends with a 1, and has that blank cell in the middle of it. The value in that cell is going to be the sum of the two numbers that come diagonally above it, which will give you 1 plus 1 equals 2. In the row below it, which is row 3, we look at those two blank cells and want to fill them, each of them, with two numbers that are diagonally above it, which is going to give you a 3 on the left and a 3 on the right. In row 4, we can do the same thing. We have 1 plus 3 equals 4, 3 plus 3 equals 6, and 3 plus 1 equals 4. We continue doing this all the way down the triangle. In row 5, we can have those blank cells be 5, 10, 10, and 5, with 1s bookending the row on either side. Why don't you take a few minutes to try to fill in the rest of the cells on your own? You should be able to pause this video long enough to do that, and then I will show you what the rest of this triangle will be. So if you did this correctly, you should have something that looks like this. Now, one thing you may notice is back in section 14.1, this notation was one that was used to describe combinations. NCR, this N over R inside the parentheses, could also be looked at as NCR from the combination section. Let's say we want to evaluate this expression here with the 5 over the 2. We're essentially asking when writing in this notation, what is the value of row 5, entry 2? Well, row 5 is this row that starts with a 1 and is followed with a 5. Entry 2 is actually going to be the third entry in the row because we're defining the value of that 1 at the start of the row as entry 0. So this comes out to equal 10, which also happens to be the value of 5C2, the number of combinations of 5 things taken 2 at a time. What about 8 choose 4? Well, yes, now that you know its combinations, you can probably just do this on your calculator. But if I wanted to find this value in Pascal's triangle, I'm going to look at row 8, which is this row down here that starts with a 1 and then an 8 and so on. And then entry number 4 will be the 70 in the middle because, again, I'm treating the 1 as entry 0. Then I've got entry 1, 2, 3, and 4. So entry 4 will be the number 70. Based on that, 8 choose 4 will be 70. The number of ways that I can have 8 things and choose 4 of them to do something without specific roles is going to be 70. Now, for 6, choose 0. We want to go to row 6, entry 0. Row 6 is the one that will start with a 1 and a 6, and entry 0 is going to be the 1 in that row. So 6C0 equals 1. Now, there are tons of unique patterns within Pascal's triangle. For example, what if we wanted to know the sum of any row of Pascal's triangle? Is there a pattern? Well, let's look at the row counts. The top row is just 1, so that sum is 1. As we work our way down, we have 1 plus 1 is 2. Then 1 plus 2 plus 1 is 4. And 1 plus 3 plus 3 plus 1 is 8. What you hopefully see here is that the sum of each row seems to be double the number that came before it. So in tying this back to sequences that we had back in the earlier parts of chapter 12, you could say that the sum of any row of Pascal's triangle is going to be 2 to the n power, where n is the row number. I'm curious as to see if you can find any other patterns in Pascal's triangle. I'm thinking that that's going to be tied to one of our discussion topics that we will have due this week. Now, we're off to look at something that would appear to be completely different, but is ultimately tied to Pascal's triangle. The problem here is asking you to identify the coefficients of each term in the binomial expansions indicated. Let's start with something simple, x plus y to the 0 power. Well, anything to the 0 power is 1. So this is going to simply be 1. If I want to look at x plus y to the first power, well, anything to the first power is just itself, so x plus y to the first power will just be x plus y. If I wanted to look at the coefficients of each term, what I would see is that I have 1x plus 1y, so my coefficients are 1 and 1. Now let's start doing some work here with x plus y quantity squared. For those who may not remember the pattern, the idea is that you're taking x plus y and multiplying it by itself. To do this, we're going to use the FOIL method, which requires that when multiplying a binomial by a binomial, you first get x times x, which will give you x squared. Then you multiply the two outside terms together, which gets you x times y. Then the two inside terms together, which again will give you x times y. Then we'll multiply the last two terms together, which will get you y squared. We can then combine the two middle terms because we call them like terms, and this will reduce to x squared plus 2xy plus y squared. Looking at the coefficients, you're going to get 1x squared plus 2xy plus 1y squared. So your coefficients are going to be 1, 2, and 1. Now let's look at cubing a polynomial. Not many people memorize the shortcut pattern, so we're going to do this one old school, or in other words, by brute force. Knowing that something cubed means it's multiplied by itself 3 times, we're going to FOIL out the first two sets of terms, x plus y times x plus y. Then we're going to multiply the last binomial, the third x plus y expression we have, by the trinomial we end up with from multiplying the first two x plus y terms by each other. So let's try this. We have x plus y quantity cubed, which we can write as x plus y times x plus y times x plus y. We already know from the previous slide that x plus y multiplied by itself will give you x squared plus xy plus xy plus y squared, because that's what happens when you use the FOIL method. Combining like terms gives us x squared plus 2xy plus y squared, but we still have to multiply all of this again by x plus y. To do this, I need to multiply each term in the binomial on the left by each term in the trinomial on the right, similar to what we did with the FOIL method, but we just need to make sure everything mixes and matches properly. One way to check that we can see that we're doing this correctly is that when we multiply a binomial with 2 terms by a trinomial with 3 terms, our resulting polynomial should have 6 terms in it, 2 times 3, before we combine any like terms. Let's take the first term by the first term. You get x times x squared will give you x to the third power. Now we'll take x times 2xy, we get 2x squared y. Take x by y squared, and you're going to get xy squared. Now it's time to look at multiplying the plus y term by each term in the trinomial. Y times x squared is going to give x squared y. Y times 2xy will give 2xy squared, and y times the y squared gives y cubed. Combining like terms together, you're going to get x cubed plus 3x squared y when putting together the two x squared y terms, then 3xy squared when combining the two xy squared terms, plus y cubed on the end. Looking at the coefficients, we see 1, 3, 3, and 1. Now let's try going to the fourth power. Essentially, we can look at this as multiplying the binomial x plus y by itself 4 times. But since we've already multiplied it by 3 times on the previous slide, we could simplify the process by taking our answer from x plus y quantity cubed and multiplying that expression by x plus y. By using what we know about x plus y quantity cubed, that will save us a lot of time. So here is x plus y to the 4th power. By definition, it is x plus y multiplied by itself 4 times. Or you could look at it as x plus y times x plus y quantity cubed. We just evaluated x plus y cubed as x cubed plus 3x squared y plus 3xy squared plus y cubed. So now we want to distribute here just like we did with the cubic, first taking x times everything on the right, then y times everything on the right. Why don't we pause here for a couple of minutes and you can stop the video so that you can try this one for yourself. Then we can go through the answer and the process. So when we do this out, the binomial with the two terms multiplied by that expression with four terms should give us something with 8 terms. Let's start by multiplying the x by everything on the right-hand side polynomial. What we'll see is x times x cubed gives you x to the fourth, x times 3x squared y is 3x cubed y, x times 3xy squared is 3x squared y squared, and x times y cubed is just x plus y cubed. Then we multiply the y by everything in that four-term polynomial on the right-hand side. Y times x cubed we'll write as x cubed y times 3x squared y will be 3x squared y squared, y times 3xy squared will be 3xy cubed, and y times y cubed will give us y to the fourth. When we combine the like terms, this will simplify as x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. Focusing on the coefficients, we have 1, 4, 6, 4, and 1. Now that we've multiplied these out, let's look for some patterns. These are the results of the multiplications we did on the previous slides. So we have x plus y to the 0 was just 1. X plus y to the first, 1x plus 1y. X plus y squared, 1x squared plus 2xy plus 1y squared. X plus y cubed is here. X plus y to the fourth was given here. What we'd like to do is generalize this process for x plus y to the nth power. In order to do this, we need to see if we can find patterns within each of the terms. Let's start by looking at the powers of x. What you should see is that the powers of x within each term start with x to the nth power and decrease in subsequent terms to go down to x to the 0 power. So for example, in x plus y to the fourth, it starts with x to the fourth, then x to the third, x to the second, x to the first, and then x to the nothing. For the y's, we don't have any y's in the first term, which could be looked at as y to the 0 power, and then the successive powers of y's increase until they get y to the nth power. So we have y to the 0, y to the first, y to the second, y to the third, and y to the fourth. I've highlighted in red the coefficients of each of the terms in the binomial expansion. What you should see is that they form the various entries of the rows of Pascal's triangle. Remember, row 0, the very top of the triangle, was just a plain old 1. Row 1, the second row of the triangle, had the two 1s in it. The third row of the triangle, which we labeled as row 2, had the values 1, 2, and 1, and so on. So what we're going to see here is that the coefficients of each term are going to follow row n of Pascal's triangle. Let's see if we can apply this pattern to the next highest power, which would be x plus y to the fifth power. As I mentioned before, the powers of x would start at x to the fifth power, and then they're going to continue their way down until we get as far as x to the 0 power, which means that there's no x's in the expression it will fall out and just be a plain old 1. For the y's, we'll start at y to the 0 power, which again would mean I don't actually have any y's there, and then we'll work our way up, increasing our powers of y until we can get to y to the 5th power at the end of the expression. The coefficients are going to follow row 5 of Pascal's triangle, which remember is not the 5th row, but it's the row which starts out 1, 5, and so on. We'll insert them here one at a time as shown until each term is accounted for. We now have this expression as shown. Now what we'll try to do is clean this up a little bit. The coefficients of 1 could be simplified so they don't have to be there, and anything to the 0 power is also 1. So this will simplify as x to the 5th plus 5x to the 4th y plus 10x to the 3rd y squared plus 10x squared y to the 3rd plus 5xy to the 4th plus y to the 5th. Why don't you try and see if you can determine what x plus y to the 6th power would be on your own for a minute? Go ahead and pause the video to try to give this a shot. All right, we're going to do the same thing. The powers of x are going to start high and work their way down. So we'll start with x to the 6th, then go down x to the 5th, x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, and x to the 0. The powers of y are going to start low and work their way up higher. So that will be y to the 0, y to the 1st, y to the 2nd, y to the 3rd, y to the 4th, y to the 5th, and y to the 6th. The coefficients of each term will follow row 6 of Pascal's triangle, where we have 1, 6, 15, 20, 15, 6, and 1. After cleaning things up, we get the following: x to the 6th plus 6x to the 5th y plus 15x to the 4th y squared plus 20x to the 3rd y to the 3rd plus 15x squared y to the 4th plus 6x y to the 5th plus x to the 6th. You may notice that if you were to add up the powers of x and y within any one term, they will always add up the power that we're raising in the expression. In the first term, you just have x to the 6th, which we could combine as y to the 0. 6 plus 0 is 6. The second term, I have x to the 5th, y to the 1st, 5 plus 1 is 6. In the third term, x to the 4th, y to the 2nd, 4 plus 2 is 6. In the middle term, 3 plus 3 is 6, and so on. They all add up to 6 because we're raising this expression to the 6th power. If we do this properly, that pattern of powers where x and y always add up to this exponent that I'm raising the expression to should always work. We can now generalize these results into what we call the binomial theorem. For any binomial a plus b and any natural number n, the expansion a plus b to the nth power can be expressed as you see here. A plus b to the nth power will be this very long polynomial. The n over 0, n over 1, n over 2, and so on, those are the binomial coefficients that are coming from Pascal's triangle. You can see within each term the powers of a start at the highest possible power, a to the nth power, and work their way down slowly, n minus 1, n minus 2, all the way down to a to the 1st and a to the 0. The powers of b start at 0, and they are going to work their way up, b to the 1st, b to the 2nd, and so on until we get all the way to b to the n. A reminder that notation with the n over a value k is really just looking at the combinations formula NCR, which can either be picked off from Pascal's triangle now, or you can generate this on your calculator using the combinations button under the math prop menu. For x plus y to the n, again, as a reminder, we're seeing the powers of x are decreasing from n to 0, the powers of y are going to decrease from 0 to n, and then the coefficients will follow row n of Pascal's triangle. And again, as mentioned earlier, the sum of the powers in any term will always add up to the letter n. Let's look at an example that's a little more complex than just x and y. Here we have x plus 2y all raised to the fourth power. The powers of x are going to decrease from x to the fourth all the way down to x to the 0, as shown here. Since what I have in my second term is 2y instead of y, we're going to look at powers of 2y, which are going to increase starting at 2y to the 0 and work their way up to 2y to the fourth power, as shown here. The coefficients are coming from row 4 of Pascal's triangle. Now we need to simplify the expression. Anything to the 0 power is 1, so the first term simplifies to just plain old x to the fourth. The second term, you've got a 4x cubed multiplied by 2y, which will give you 8xy cubed. In the third term, the coefficients are 6 times 2 squared, which is 6 times 4, or 24. The variables are going to be x squared and y squared. Next, we've got 4x times 2y all cubed. The coefficients become 4 times 8, which is 32, and the variables are going to be x to the first and y to the third. In the last term, the 1 and the x to the 0 fall out, and you're left with 2y all raised to the fourth power, which will give you 16y to the fourth. Let's look at a few more examples. I put the binomial theorem here in sigma notation so that you can see where things are coming from. Here we see that we're going to be summing up from k equals 0 to k equals n the expression n choose k, which gives you the coefficients from the binomial and Pascal's triangle. Then you've got powers of a, which are decreasing from a high of n to a low of 0. Then the powers of b are increasing from a low of 0 to a high of n. This example has a minus in it. Since the formula for a binomial expansion assumes we're going to be adding two terms together, we're going to say that the second term in the expansion is going to be -3. So we're going to be treating it like 2x plus -3. Following the pattern, just like before, the powers of the expression 2x are going to start at the high power of 2x all to the fifth power and work their way down to 2x to the 0 power. Then we're going to look at the second term, the -3, which we're going to treat as a -3 and raise that to successively increasing powers, starting at -3 to the 0 power and ending with -3 to the fifth power. Since we're raising this binomial to the fifth power, we're going to take our coefficients from row 5 of Pascal's triangle to get 1, 5, 10, 10, 5, and 1. Now let's try expanding and simplifying this out. In the first term, we have 2x all raised to the fifth power, which will give us 32x to the fifth. In the second term, our coefficient is going to be 5 times 2 to the fourth, which is 15, times negative 3, which becomes negative 240. For the third term, you've got 10 times 2 cubed times negative 3 squared. So that becomes 10 times 8 times 9, which will become 720. Next, we have 10 times 2 squared times negative 3 cubed, which reduces to negative 1080. Continuing, we have 5 times 2 times negative 3 to the fourth power, which is 81. So 81 times 10, 5 times 2, will be 810. Lastly, negative 3 to the fifth power is negative 243. The powers of x are just going to be working their way downward, x to the fifth, x to the fourth, x to the third, and so on. So here is our final answer expanded. 32x to the fifth minus 240x to the fourth plus 720x to the third minus 1080x squared plus 810x minus 243. Now let's see what happens if our second term isn't something simple with a y in it. The process is going to be the same. We're going to start with powers of 3x squared that will be decreasing as we progress. So I'll have 3x squared cubed, then squared, then the first, and to the 0 power. The powers of 1 over x are going to start at the 0 and work their way up to the third power. The coefficients are coming from row 3 of Pascal's triangle. Then we have to expand everything out. In the first term, 3 cubed is 27, x squared cubed is x to the sixth, and then in 1 over x to the 0 will just be plain old 1. In the second term, 3x squared squared will be 9x to the fourth. In the third term, we have 3 times 3x squared times 1 over x squared. And in the last term, we'll have 1 times 1 times 1 over x cubed. Simplifying each of those terms gives us the following. I'll have 27x to the sixth plus 27x to the third after multiplying the 9 times 3 and the x to the fourth by 1 over x. In the third term, I'll have just a plain old 9 because 3 times 3 is 9, and x squared times 1 over x squared will cancel, leaving x to the 0. In my last term, I'll just have 1 over x to the third. The last type of problem we'll look at here would be one if you were asked to find a value of a particular term in an expansion, but not the entire expansion. For example, if I was to ask you to expand something to the 10th power or the 12th power and list off all the terms, it would probably take a long time, and you'd probably contemplate dropping the course after having done 1 or 2 of those. In the alternative, when working with those larger polynomial expressions, what I might ask on a homework or a quest would be to find a particular term in the expansion rather than expand on the entire polynomial. What we're going to have here is that the k plus first term of the expansion a plus b to the nth power is going to be n choose k times a to the n minus k power and b to the k power. Now, this looks intimidating, and when written like that, I can agree with you. So let's perhaps look at this from a simpler perspective in the context of a concrete example. Say we want to find the fifth term of the quantity 2x minus 3y raised to the 8th power. If I want to get the fifth term, we're actually going to use k equals 4 because the fifth term is what's going to give us 2x raised to the fourth power and negative 3y raised to the fourth power. Think about it. If we were doing this by brute force, we'd start by decreasing our powers of 2x 5 times. So I'd go 2x to the 8th, 2x to the 7th, 2x to the 6th, 2x to the 5th, 2x to the 4th. For the y's, we'd increase from 0, giving us negative 3y to the 0, negative 3y to the first, negative 3y squared, negative 3y to the third, and negative 3y to the fourth. From Pascal's triangles perspective, we would go to row 8 and start reading along until we got to entry 5, which would, again, remember the first entry is actually entry 0. We would look at 1, 8, 28, 56. So ultimately, this is going to simplify to 8c4 times 2x raised to the fourth power times negative 3y raised to the fourth power, or 70 times 16x to the fourth times 81y to the fourth, which if we break this out on our calculators is going to give us 90,270 x to the fourth y to the fourth. Let's try one more and then we'll wrap this up. Here we want the eighth term of the expansion, x plus 2y to the 12th. Again, if I want the eighth term, I need to back up to k equals 7 because my first entry in the row is actually entry 0. So everything will be off by 1 otherwise. The formula, when applied here, will look like 12c7 times x to the 5th power times 2y to the 7th power. And if you're still having some easiness with this, or uneasiness with this, that's okay. Let's think about using the brute force method. If we were doing this out by hand, and I asked you to find the eighth term within that expanded polynomial, we would start our powers of x and work our way down 12th, 11th, 10th, 9th, 8th, 7th, 6th, 5th. That would be the eighth term. We'll have an x to the 5th in it. For the powers of 2y, we would start at 0 and work our way up. So to get to the eighth term, I would have y to the 0, y to the first, y to the second, y to the third, y to the fourth, y to the fifth, y to the sixth, y to the seventh. So this expression, the eighth term, would be having a 2y to the 7th power. From there, we go to Pascal's triangle, row 12, and we go across the row. And we'll see 1, 12, 66, 220, 495, 792, 924, and 792. Plugging these values in and expanding the powers, you now have 792 times x to the 5th times 128, which is 2 to the 7th, times y to the 7th, which will multiply out as 101,376 x to the 5th, y to the 7th. So that's it for section 12.6. Here's the problem challenge for this section. Don't get too intimidated by everything that you saw in here. Ultimately, there's only one formula that we're working with, and that's the binomial theorem. And there are a lot of patterns that you can follow, so you don't actually need to memorize the formula at all. I personally will tell you that I'm not a formula person as a rule because I'd rather focus on the patterns and uses rather than dealing with memorizing a formula that may otherwise make no sense in context. Go ahead and give these problems a try, and if you have any questions, go ahead and send me an email, or better yet, post it on the discussion board. Thanks for watching, and we'll see you all soon.